Okay, this is going to be a short screencast to get across to you guys the ideas behind what Brody and Brody 1990 are doing with their data. Oftentimes, students are confused by the idea of residual resistance to tetrodotoxin and what mass-adjusted resistance is. And so what I did was I created a fake data set in order to kind of show you what they're doing, even though these aren't their actual data. So I'm in R, and basically I've just created a data set called residual example, and you can see that it has baseline speed and post-injection speed, and then it has mass. So when the Brodies were trying to quantify resistance, they measured the baseline speed without being affected by tetrodotoxin, and then they measured the speed of those same snakes after being injected with tetrodotoxin. And that regression ended up being positive. And when you look at what it looks like, you can see that faster snakes are also faster after they've been injected with tetrodotoxin. But you see that these snakes up here are all greater than 50 centimeters per second. But these snakes, after they've been injected with tetrodotoxin, are below 50, which means tetrodotoxin has had an effect on them. But still faster snakes, even under the influence of tetrodotoxin, are still faster than the slowest snakes, even if a slow snake isn't affected by tetrodotoxin at all. So what they want to do is they want to remove the effect of baseline speed, and they're going to do that by essentially calculating what the residual values are. Remember that the residual value is the difference between the value of the data point and the line. So if you go straight down from the data point to the line, that's the size of the residual. So some individuals have residuals that are really high. That means that they're really resistant regardless of their initial speed. Some individuals have low resistance because they're far below the line, once again, regardless of what their initial speed was. So in R, we can actually have R calculate those residuals for us, and we can store them so we have residual resistance. And now when we look at baseline speed, which is right here, versus residual resistance, hopefully we've removed the effect of baseline speed. And so when we look at that plot, we see that baseline speed varies a lot, but residual resistance is not correlated with it. So these individuals up here are highly resistant, even though they started out at a high baseline speed. They're still highly resistant. But this individual here is also highly resistant, even though he started out at a really slow baseline speed. But then they also had to worry about whether or not mass had an effect on residual resistance, because the bigger you are, the more likely you are to just be able to absorb a large amount of toxin without experiencing the negative effects of it. So when you look at mass versus residual resistance, you see that there's still this correlation there, such that bigger snakes tend to have higher levels of residual resistance simply because of their size. Smaller snakes have lower residual resistance because they're just small. Well, we can do the same thing that we did before with baseline speed and post-injection speed. We can look at how residual resistance is affected by mass, and we can save the residuals from that model. And now we have mass-adjusted resistance down here at the bottom over here. And then we can take that mass-adjusted resistance and regress it against mass, and hopefully what happens is we've gotten rid of that relationship. And once again, you can see that the slope value is very near zero, and when you look at a plot of the data themselves are now not correlated with mass anymore. So you now see mass-adjusted resistance varies a lot, but it doesn't vary systematically with mass. Some individuals are high mass and also high resistance. Other individuals, though, are also high mass and low resistance. Some individuals are low mass and high resistance, and some individuals are low mass and low resistance. So you've effectively removed systematic variation due to mass and systematic variation due to baseline speed in getting at what is hopefully an unbiased estimate of how resistant any given snake is, regardless of how fast they started out and regardless of how big they are. Hopefully this helps you understand what the Brodies are talking about when they talk about mass-adjusted resistance. And that's it.